Yes, the recording has started. So yeah, all right. Let's see what we will do today. LA DFT. We'll do DFT, and today is week 11. The date is 28th of October, 2024, Monday, and we are doing tutorial DFT question number 5 and question number 6, and then we are done with DFT. Okay, let's flash out the questions today. All right. Hey, I guess someone hasn't unmute, so I need to mute some of you. Okay, thanks. All right. Okay. Mm, we'll just wait for. Okay, I'm going to ask you one more time. If you're, yes, you guys can hear me. Good. Right, may I start? Everybody? Great, thank you. Okay, let's see the questions first. Welcome back. So the questions is this. This is the tutorial 8A questions. I'm going to answer question 5A, 5B, 5C first. And the questions basically are the standard questions that we would ask for DFT. So 5A is a question called analysis, DFT analysis. And it's analysis because we are asked to find the big X given that we have this given the small x. And you realize that this is the problem that we are being asked to find. 2003 and then therefore what is W? And W is the DFT matrix. And let's see the sizes first. Our input is 4 by 1. Our DFT matrix is 4 by 4. And therefore our output is 4 by 1. Now, the other thing that you have to note is this, is that the input is a real vector. And the output is a complex vector. And the reason why it's complex is because the W matrix is complex. So the only unknown that we have here is W. So let's carry on and then find out what we can write about W. So X is equals to, and the W you realize is, I'm going to write this equation and you must memorize this, 2 pi over n k n. And this is 2003 as usual. And let's be very clear about the notation. This is small x0, small x1, and here is small x3. And this little bracket here is n, running from 0 to n minus 1. And our capital N is equals to 4 because our input is a 4-element vector. If this is the W matrix, so now I've given you more information on what is the W matrix, and W matrix looks like this. So the only unknown now is K and N, because big N is already given, which is 4, and the only unknown is little k and n. So where am I going to run K and where I'm going to run N? So the key idea is this. N the little n is running from top to bottom. Small n is running. Therefore, this matrix W must be running n equals to 0 to n minus 1 along the what do you call that? For each row, we are running values of n, from n equals to 0. And let's see what and let's see what x is. Okay. So this is oops. This is big X 0, big X 1, big X 2, and big X 3, big X. And here is the index k. So therefore, k is running from 0 to n minus 1 as the row of W is progressing. So now we know how k and n should be put in. Once we have done that, then now we can write our matrix. Okay, so let's start with k equals to 0 first. So this is e minus j 2 pi over, and our big N is 4. A is 0, right? Because we are running at the first row. And N is 0. So let's complete the entire first row first. E minus j 2 pi over 4. K is 0. N is 1. E minus j 2 pi over 4 is pi over 2. K is still 0. N is 2. The last one, E minus j 2 pi over 2. Pi over 2, 0, 3. So we have done the first row of the W matrix. And then now do the second row, E minus j. So here is k equals to 1, pi over 2. Okay, let's simplify. 2 pi over 4 is pi over 2. K is 1, N is 0. Second one, E minus j, 2 pi over 4, k is 1, N is 1. E minus j, 2 pi over 4, k is 1, N is 2, E minus j, pi over 2, 0, 3. And then you can complete the rest, right, guys? I don't think I need to do this. And we're done for W. Now, let's substitute the values and calculate this matrix. So let's fill up this value. E minus j to the power of 0, because 0 times anything 0 is 1. Here is e to the power minus j times 0 again, which is 1. 1, 1. So this number is very easy to fill, the first row. Now the second row is the most exciting row, because the first element of the second row, or k equals to 1 row, is e to the power minus 0. So it's still 1. You think it's not very exciting, but here is the most exciting part. E minus j, 2 pi over 4 is pi over 2. So this guy is actually e minus j pi over 2. What is e minus j pi over 2? It's the same as 1 angle minus pi over 2. So I want you to draw a circle now. And this is the real value, and this is the imaginary value. And tell me, where is e minus j pi over 2? Or I prefer this. The absolute value is 1, because this is 1 exponential. Angle is minus pi over 2. So isn't it here? This vector, the green vector, going down, unit is 1. Actually, when we are going along the imaginary, the unit is, here's minus j. So this vector is actually minus j. Can you all see, guys? Yes? Now, if you can see this, then realize that the second element is minus j. Now, you compare to the first element, is 1. Where is 1? I'm going to draw for you. This is 1. The original vector is here. So this is 1. 1 is the blue guy is here. The green guy is minus j. Now I'm going to draw the red guy for you. Where do you think the red guy is? So let's see the equation again. E minus j 2 pi. 2 times 2 is 4. So it's minus pi. So it is E minus j pi. What is E minus j pi? It is 1 angle minus pi. So let's draw E 1 angle minus pi. So I have to have a different color. Oops, I have no more color. Oh, let me find a color. Let's find orange. So this guy is 1 angle minus pi. So why minus pi? Means that it rotates clockwise. Rotates anti-clockwise, plus pi. So actually it is also equals to 1 angle pi. Doesn't matter. It is also equals to, guess guys, I'm going to write. This is 1 minus pi. 1 angle pi. It is also equals to minus 1 plus j0, right? Because the blue is 1. This guy is minus j. This guy is minus 1. This guy is plus j. So it is actually minus 1. So it is equals to minus 1. So I'll erase all this now. And I'll write minus 1. So where do you think the last guy is? So you already see a pattern. We begin with the blue. We're moving from here to here. We're moving by pi over 2 radian per sample. Minus pi over 2. So we are moving clockwise. Here to here, same. So every step, we're moving by minus pi over 2. Can you see the blue to the green? Minus pi over 2. The green to the orange? Minus pi over 2. So the last one, and I guess you should be able to guess it by now. We move here. It should be plus 1, plus j. Okay, now let's not get ahead of ourselves. Let's go and see our equation. This is e minus pi over 2 times 3. This is 1, guys. So this is e minus j pi over 2 times 1 times 3 equals to e minus 1. 3 over 2 is 1.5 pi minus j 1.5 pi. Minus j 1.5 pi. Yeah, we are rotating 1.5 pi to reach here, and we have reached the next blue guy. So now we can see the 4 numbers. 1 minus j minus 1 plus j as this row. So this is the row K equals to 1 of the W matrix. And the W matrix is the DFT matrix. Okay? Now, so it took us, what, 10 minutes to fill up this guy. In the exams, you have no chance to take 10 minutes and fill up this guy. Okay, so I'm going to teach you something easier to memorize. And then we'll fill up this guy very quickly. So once we have this, then we can fill up the next row, which is, so you realize that the first column is all 1. This guy is the most interesting guy. The next one, 1. What do you think this value is? It skips. 1 become minus j minus 1. Now we are talking 1 to minus 1. That's how we actually see the change. Okay, so instead of taking one step at 90 degrees, I'm taking one step at 180 degrees because this is k equals to 2. So if I take another 180 degrees, it is plus 1 again. Another one, minus 1. Okay? What about the last row? The last row, so this guy is taking 90 degrees. So it's one step. This guy is taking 2 steps. This guy, the last row, is taking 3 steps. So it's 1 plus j. Then what do you think happened? It takes 3 steps again. So it will become minus 1 minus j. So this is how you draw the W matrix. And once you have drawn the W matrix, then you are going to put the elements 2003 here. 2003 here. So this is W, this is small x, and then now we can find the big X. And the idea is very simple now. We just need the first element, which is non-zero, times this guy. So I'm going to write down 2 times 1, 1, 1, 1. So this is a matrix vector multiplication. The non-zero elements here is multiplying by the first column. The second one is 0, so it's multiplying by this. We don't care. The third, the third element is multiplying by this column, and the fourth one is plus, I should write in red now, 3. So it's this 3 times this guy, which is 1j minus 1 minus j. And now, of course, you can just add up the values. So let's do it. 2 times 1 is 2 plus 3, 2 plus 3j, 2 minus 3, and 2 minus 3j. And of course, the answer is 5, 2 plus 3j minus 1, 2 minus 3j. Okay, did I get it right? 5, 2 plus 3j minus 1, 2 minus 3j. Okay, so this is question 5a. So let's look at the question again. The question is very, very short. It just says, I give you a vector 2003 transpose, which is this guy, 2003 transpose. I'm asked to find the DFT coefficient, which is that big X we're interested in. So this guy is a DFT coefficient. And n equals to 4. So n equals to 4 basically means that the X element has 4 elements and the W matrix is a 4 by 4 matrix. So the unknown is the W matrix and we fill it up. Once we fill it up, then we are doing matrix vector multiplication. That's all. We are doing DFT already. Okay, so I'm going to, so this is the DFT matrix. I will now show you some slides which I've prepared. So in the lecture, this is the slide that you should be looking at, page 20. Here's the generic DFT matrix. It is an n by n matrix. You'll see that I'm writing k is running around here, n is running around here. And for different k and n, these values comes up. The thing to remember is that the elements of W is E minus, okay, minus is the keyword, minus J 2 pi over N Kn. Once you have this memorized, you can fill up the matrix. Actually, I mean, if you want to go and memorize this, of course, if it is the question is 4 point, then it's the same. This is the DFT matrix. Okay, so when you recognize DFT matrix, see it as rows in the DFT W matrix. This is all 1 as the first row, 1 minus j minus 1j as a rotating phasor. Okay, so I repeat, where's my rotating phasor? Oops, it's gone. As a rotating phasor clockwise. Now I'm going to show you some MATLAB code to run, okay, so that you can visualize. Let's see if I can run my MATLAB code. Okay, I'm going to use n equals to 4 first. And I'll run my MATLAB code. I'm producing a unit circle and the phasor. So when it is running like this, the phasor, it means that the amplitude is 1, 1 along the real axis. Okay, so how to interpret this circle? Let me draw for you again. This, this is my real axis. This is my imaginary axis. I will draw a circle. So let's fill up the number first. This is 1. This is 2. This is -1. This is -2. So this is the real line. This is J. This is -J. I will draw the circle for you now. This is called the unit circle. Now, if I want to draw a phasor, and I'm going to draw a phasor using blue, this phasor is, let's call this Z, is equals to, you can write it as 1 because this is only 1, or you can write it as plus J0. You can also write it as polar form 1, angle 0, or you can write it as 1 EJ0. All three representation represents this same phasor. In fact, you can also write 1 EJ 2 pi. This is 1 EJ 2 pi times K. Doesn't matter because when you're rotating by 2 pi, you are still back into the same point. So these are all the ways you can draw this phasor in the complex plane. So I'm drawing this circle and this phasor. So okay, there's one of y'all whose mic is turned on. Can you all turn it off, please? Okay, and then now you can see all 1, 1, 1, 1, 1. What about this guy? The second row of the W matrix is 1. And when you come down, right, what are we doing? So I'm now going to draw for you the second phasor. And when we come down, this is -J, right? So Z is equals to, coming down is -J. It is pi over 2 negative. So this is equals to 1, or I should write 1 angle minus pi over 2, or I can write 1 E minus J pi over 2. All these three notations are the same, talking about this same vector. Minus J pi over 2, or 1 shorthand minus pi over 2. Minus means clockwise direction. So this is the second one. So the first one is 1, the second one is minus J, the third one is -1, right? Let's go and see this again. I'm going to use blue again. So this blue guy is pointing at -1. So this Z is equals to -1 is equals to -1 plus J0 is equals to 1. The length is 1. Angle is minus pi because I can rotate minus pi, or I can say 1 angle pi. Doesn't matter. Whether I rotate positive way or the negative way, I will still reach the same point, which is -1. So -1 is actually very confusing to some students. So see, this is -1, and finally we have plus J. So this is a very nice diagram showing you how we can interpret the rows of the W matrix. Now, this first row is the most interesting one. And I'm now going to use a different n for you. Now I'm going to increase from n equals to 4 to 8. Please remember, each step I'm making by pi over 2. Why pi over 2? Why am I moving by pi over 2 each step? Because it's 2 pi over 4, pi over 2. So that E minus J, 2 pi over 4, K, n. K is 1, right? You see? Here is the key number. 2 pi over 4 means that if I'm using K equals to 1, I'm moving by pi over 2 radian per sample. What happened when I do E minus J 2 pi over 8? K is 1, n equals to 0 to n minus 1. Then you'll realize that I'm moving by pi over 4. How big is pi over 4? It's 45 degrees. Now let's see the first row, okay, as I change n equals to 8. What you will see is that as I increase my n, then my phasor is rotating still clockwise, but now at 45 degrees. So only at 2 steps, it makes 90 degrees. Just now, in 1 step, I already make 90 degrees. Now, in 2 steps, I will make 90 degrees. In 1 step, I make 45 degrees. Let's increase n further. N equals to 16. Let's observe this. So you can see the phasor is rotating. And in the 15 sample, 0 to 15, it almost make it the whole round. At the 16 sample, you will hit back exactly the first point. So the first row, k equals to 1 of the W matrix is the most exciting one. It tells us how many samples is required to make one complete revolution for the complex exponential. Okay, so this is the W matrix in a phasor. We are seeing it as a phase rotations for different places in the WJ from the different places K and N. Right. So I know that I took a lot of time just to do the first question, but once you actually understand this, then the rest is really quite simple. Okay, now we're going to do the second question now, which is the inverse of the DFT. Okay, so let's see the question first. So in question 5b, I am given big X equals to N, and I should write it as here, 0, 3e minus j pi over 4, 0, 0. And I will ask to find small x. Okay, via IDFT. So let's write the equation first. We'll write two equations. Big X is equals to W small x. Therefore, W minus 1 big X equals to W minus 1. This becomes I equals to small x. What is W minus 1? It is equals to 1 over N WH, or conjugate transpose. Therefore, small x is equals to 1 over N WH times big X. Oops. Oh, sorry, I'm not displaying what I'm writing. I repeat. Let's start with the equation we know. This is the analysis equation. Big X is equals to WX. If the inverse of W can be found, and it can be found because W is a square matrix and it has independent rows and columns, which is full rank. Its inverse exists. So we left multiply by the equation with W minus 1. So it's W minus 1x. So W minus 1 W becomes identity small x. So now we are left to find what is W minus 1. Without showing you the proof, I will tell you now that W minus 1 is 1 over N WH. And WH is nothing but the conjugate transpose. So this is the conjugate transpose of W. And then we have this equation over here. So now I'll show you what if you are short of time, what should you do? Okay, I repeat. If you are short of time, all you want to write is this equation. X equals to 1 over N WHX. This is X, small x. 1 over N, 1 over 4. This is the big X. So what is this matrix? This is conjugate transpose of the above matrix. This is above matrix is W. What is conjugate transpose? It means that you bring the rows as column. So all this 1 becomes all this 1. This guy, 1 minus j minus 1j, becomes this column, 1, but is conjugate transpose. Transpose is easy. The row becomes the column. Conjugate means that the imaginary number is conjugated. Minus j becomes plus j. Minus 1, no change. J becomes minus j. So 1j minus 1. So you realize that because the matrix is symmetric, actually it is nothing but just conjugating every elements. So that's it. 4-point DFT. Once you have this equation, all you're doing is to plug in our x, and you have this matrix W and 1, 4. Now let's try. Okay, so I'm just going to write this for you now. The small x, which is small x0, small x1, small x2, small x3. So again, n is running 0, 2, n minus 1. I'll write the IDFT matrix now. So it is 1 over n. Okay, our n is 4 in our question. I'll write all the elements of the W matrix. And now I'll write the big X. What is my big X again? What's my question? Which is 0, 3e minus j, 0, 3e minus j pi over 4. So it's 0, 3e minus j pi over 4. The rest is 0. Now, when we give you questions like this, with so many zeros sitting around, you realize that the first 0 is scaling this guy. Oh, I forgot times n. There's a times n. Remember, the coefficients I'm giving you is n times this. So I put the n at the back. Now, you realize that this n will cancel with this n. So the n's gone. This 0 is multiplying with the first column. Useless. This first column is not used. So it is nothing but I'm using this column scaling by this number. So the answer is 3e minus j pi over 4, this number 1j minus 1 minus j. And of course, you guys then go and open it up in polar notation and multiply together. That's it. This is the answer. So to perform IDFT, to perform DFT, all you need to do is to remember these two equations, at least for n equals to 4. This is the matrix W, this is the WH matrix. Any questions so far, guys? Okay, let me see my chat. Any questions, guys? Can you share the MATLAB code? Yes, yes, I can. Where the n on the right formula come from? Okay. Look at the question. Given x equals to n. Can you see the n there? Chok Hong. Is there a good way to remember the rows and columns of W is K or N? Yes, there is. Okay. Actually, you don't really need to care because the matrix is actually symmetrical. But let's say we care. And if we care, let's start with the DFT matrix first. Big X is equals to W small x. As we are naming this small x, we are running small n. So this is definitely n that is running along the downwards. Now, when you look at the big X, we are actually taking this row, these elements along the rows, and we are actually inner producting with this guy. So therefore, the elements along here must be called little n in time. Is that clear, Ignatius? And if this is time, therefore this must be frequency. Again, you know that this is frequency k, because on the left-hand side, we're talking about big X, 0, 1, 2. So why do we call k the frequency, guys? Why do we call k the frequency? Let's see. Let's see this. Where is k? It is e minus j 2 pi over n kn. So all these guys are k. I'm highlighting, yeah? All these guys are k. So all these guys are k. Now, what is k equals to 1 means? Then the n is always running, right? Along the rows. It is scaling this guy. The next one, I'll show you now. E minus j 2 pi over 2 times 2 dot 0. E minus j 2 pi over, 2 pi over 4 times k is 2 times 1. So you notice that e minus j 2 pi over 4, this guy is the fundamental frequency. K is the harmonics. As I increase my row of k, I am making the vectors, the row vectors, rotating faster and faster. Okay, that's it. So we call it the k harmonic. Therefore, each element of this big X is actually telling me the contribution, okay, or how important is this frequency for different harmonics. The larger the value means that my X is more related to that frequency. That's the interpretation. W first, Benedict, W is always symmetrical because you look at this. K and N, we swap around, doesn't matter, right? So K and N is definitely symmetrical. Okay, does that answer your question, Benedict? K and N. Okay. So going from different rows, I think you better look at this picture. Where is N running and where is K running? This picture versus this picture. This is the IDFT. 1 over N WH. Then this is the big X. Remember X, the big X is always running different Ks along here. Therefore, this guy must be K. This is one way to remember it. The other way is look at the left-hand side. This is small x. Small x is always running from x equals to n equals to 0 to big N minus 1. Therefore, this guy, each of these row of the WH must be also running time because otherwise it doesn't make sense, right? On the left and right hand side. Okay, with that, I'm done with question 5A and 5B. Now, 5C, I think I've shown you the solution, right? Again, if you know how to do 5B, then 5C is trivial, right, guys? So let me write the question first. 5C, I am given xk, and I'm given n, and I'm given 2, 3e minus j pi over 4, 0, 0. So I'm given this, and I'm asked to find small x via IDFT. And again, small x is equals to 1 over n WH 2, 3e minus j pi over 4, 0, 0. And we have n here. This n came from this n. And again, we cancel. And then all we are left to do is to find the first column 0 of WH plus 3e minus j pi over 4 column 1 of WH. And then you just construct the WH for column 0 and 1 because you can ignore the rest because the rest is 0. So don't go and write in this example 16 numbers, right? You just write 4 numbers for column 0 and 4 numbers for column 1. So that's the trick. Is X always in a real space? Yeah, no. Here X is complex. Can you see? Yeah, here X is complex. And it does work. Yeah, see? The first column of WH is complex numbers. So actually I lie. Well, I didn't lie, but in some examples, X can be complex as well. Okay? What is the suggestion? Xn via inspection. Yeah, this is the suggestion how to find X by inspection. We know we know the equation for inverse DFT. And we know that most of the values are 0. Therefore, we only need to construct the corresponding columns of WH. That's it. This is the final answer. And of course, in the exams or in the quiz, we'll give you some vectors and ask you to compare, and you have to tell us which is the answer, right? Okay. So now I'm done with question 5 ABC. Any questions, guys? If none, then I'm going to go to question 6. All right. Question 6. Let's discuss. N now is 16. So let's always write. And then we are going to describe W. So it means that X belongs to C16 or R16. Okay? We allow the input to be complex or real. And W is 16 by 16. And X is 16 by 1. And this is a complex vector. So W is square, 16 by 16. So that's the first thing we can tell about W. Second thing we can tell about W, guys? Anyone? Please help. What did I write? Okay, this is what I write. Okay. So the second thing I wrote is the elements of W, element of W is equals to E minus J 2 pi over 16 Kn. Okay, this is the element of W matrix. So remember it's minus, huh? What else I must write? 3. The rows of K, the kth row of the W matrix is used to compute capital back XK. Row K, right? Row K of W. I'm using the row K of W. See, you look at the matrix here. And if you are looking at the matrix and you are seeing that this is the kth row, we are multiplying by the small x to give you the XK element. So the XK element is the inner product of the row K with the X. That's why the row is interesting. We are viewing the row K of W to see what it is. Okay, what else can we say? We can say many things. The fourth is because it's E minus J 2 pi over n kn. Therefore, W is symmetrical. Why symmetrical? Because you swap K and N. Doesn't matter. The elements will still be is commutative, and then therefore the matrix still remain the same. NK, KN doesn't make difference. And what is its inverse? Okay, I never proved to you, but actually the rows of W are orthogonal. Okay, I never proved. You go and check it out. Each row is orthogonal. And therefore, 6 happen. The inverse of W is 1 over n WH. And WH is what? Conjugate transpose. This is 1 over n W bar, which is the conjugate transpose. So W bar means conjugate of W. Transpose means the matrix is the rows become the column. So H is the representation of this W bar transpose. And this is because of this property. The rows of W are orthogonal. Okay, what else? 7. The row 1 of W is what? Is a sequence of what? Rotating phasor of what? Amplitude equals to 1. What else? Rotating clockwise or anti-clockwise, guys? The first row of W is a phasor, right? We know it's a phasor. It is going to rotate clockwise or anti-clockwise. Clockwise, very good. By how many radian per second? Per sample? By 2 pi over n radian per sample. Yeah, capital N, guys, not small n, must be capital N. All right, see, we can understand so many properties now, right? Okay, now this is very difficult to understand, but you have to do it by yourself. Row n minus 1 of W is what? A phasor rotating what, guys? If the top is rotating clockwise, the row n minus 1, I'm talking about, is rotating anti-clockwise by 2 pi over n radian. Now, this is very strange, right? Guys, you think the first row is rotating clockwise. The last row is rotating anti-clockwise. Why? Let's go and run our MATLAB again as usual. Okay, you can see. This is the MATLAB diagram. The first row, row 0, doesn't rotate. The first row rotates clockwise. In here is 16, right? So every time it's rotating a little bit, a little bit, a little bit. Let's look at the last row, guys. Hey, he's rotating like the first row, k equals to 1, but he's rotating the opposite direction. And he appears to be rotating anti-clockwise. Can you see? Nice, huh, guys? Okay, so yeah, I'll release this MATLAB code and you guys can play with it. How's that? All right. Okay, and I'm done with 6a. So I have described to you the DFT matrix. I've also provided the equation to represent the kth row, right? Nothing else. I've also explained how is the kth row related to xk. So I've done a lot. So only the last 2 questions now, guys. Okay. Question 6D. Small n equals to 3ej 2 pi over 16n plus pi over 3. All right. Guys, please be careful with the brackets. This J bracket everything here. This is not the same as, not the same, huh? The same must be what? It's not the same, not the same. Okay, please don't write this and expect us to interpret that this is okay. It's not. So please write. Please put a big bracket. So what do you think xn is, guys? And then I told you that n is 16. So I'm expecting to see this x0 equals to 3 ej. What? The n is 0, right? So it's 0 plus pi over 3. And this guy is 3ej pi over 3. That's the first element. Second element, 3ej. Now I can put 2 pi over 16, which is pi over 8 times 1 plus pi over 3. So you realize that this pi over 3 is always added to this guy. Now, pi over 8 times 2. So the general equation is xn is equals to 3ej pi over 8 times n plus pi over 3. Right? Same equation as above. Oops. That's the idea. It is a vector of how many elements? Vector, a complex vector, right, guys? This is a complex number. C, n. C, and n is 16. Right, so I have a complex vector. And this is very interesting because I know that this vector 2 pi over 16, ej 2 pi over 16, is actually one of the row of the W matrix. Or is it WH matrix? Okay, so therefore, how should I tell you this? I'll show you the answer. It's a bit hard to explain, really. So this is the answer, guys. If I have given you xn, if I given you xn, oops, if I given you xn and I ask you to find x and I asking you for a vector of 16 numbers, this is going to be very expensive to do. You have to construct xn like what I did. You have to find the W matrix, which is a 16 by 16 matrix. By the time you fill it up, it's like 10 minutes. And then you have to multiply. It's going to be so expensive. So we'll never do this, right? Unless you are using MATLAB. So what should we do? We recognize that xn is a complex exponential, exactly one of the column of WH. And we know that the columns of WH is orthogonal. And therefore, when we are doing W multiplied by this guy, only one number will come out. Okay? And the number is exactly at k equals to 1. That's the key idea, right? Because the rows of W are going to be orthogonal to X. Therefore, the only interesting row that will multiply with this guy is the first row of W, which is the first column of WH. That's what I'm writing. And therefore now we will, I'm just going to skip the rest and I'm going to tell you the answer, which is that only x1, the first row of W multiplying by my x, will produce this number. And this is the answer, x1. Okay, and the rest of the values are 0. And how am I so sure? And it's because let's go and plug all the x zeros to be 0 here. And if I construct WH, since this is all 0, it's all gone. WH, therefore the only interesting column of WH is the first element, k equals to 1. The first column, k equals to 1 column of WH is interesting. Again, n divides, and it is 3ej pi over 3 times the first column of WH. And then the first column of WH, voila, is exactly my equation of xn. Okay, that's the key. That's the answer. All right, now 6e, maybe I would record it and I will give to you because it's running late. In very brief, I'll show you that 6e is a sine wave, and a sine wave can be constructed as two complex exponential. And these two complex exponential, since we have done one complex exponential, then it's simple to do two complex exponential. We'll find that only two elements are non-zero to find the big X, x1 and x15. And in fact, they are very interesting. They are phases rotating at the opposite direction, but the same radian per sample. That's the key idea. Okay, with that, I think I'll record this maybe one more time, and I'll put it up in the lecture, in the solutions again in a few days. Now, with that, let me stop here and ask you all if you have any questions. Is there any penalty? Well, we prefer to, but because it's MCQ, guys, so what happened is that you have to select the answers from our MCQs, right? For the quizzes and everything, and the exams as well. Eben asks, is it because the rotation frequency is so large that it appears to run opposite? Yes, that's right. It's called aliasing effect. Anything else, guys? Anyone? What will we be doing on Friday? We would begin eigenvalue and eigenvectors. Are there any practice papers? No. Why do you need practice papers? You you can do all the tutorials. That will be your practice papers. Any shortcut to what? DFT? Yeah, the shortcut is this. I'll show you the shortcut. The shortcut is this. If it is a 4x4 matrix, a 4x4 problem, you need to memorize these two equations. That's the shortcut. If the elements are mostly zero, we are interested in only the corresponding columns. That's the other shortcut. If I'm giving you n equals to 16, never draw this W matrix or W matrix or WH matrix. Impossible. Okay, who else? I'm answering all the questions now. For question 60, why is that the only first column of X have output? No, it's not the first column of X. The first, uh, in this question, the equation is a complex exponential rotating at 2 pi over 16 times n. You'll recognize this as actually one of the columns of, the one row of the W matrix. When we multiply, when we cross product this, we'll exactly get the coefficients 3ej pi over 3. 3 comes out, pi over 3 comes out. This guy is cube. Okay, so here. And the rest of the rows of W are orthogonal to this guy. So when we try to inner product with this, out comes 0. So that's what we're saying here. Okay, so this is the reason. Hey Ben, does that answer your question? You have to try, okay? You have to try. Try it by yourself. Try n equals to, keep capital N equals to 4, and you know what I'm talking about. Any other guys? Did I go very fast today, or is it okay? All right. Okay, it's definitely 5:30 now. We're running out of time.